Did you start it?
Yes, it started.
Okay, great. So it's a great pleasure to have Fabio Apruzzi from Bern/Padua or Padua/Bern, and he'll tell us about non-invertible symmetries from holography and branes. Take it away.
Thank you for the very nice invitation to speak at the Symmetry seminar. And yeah, so this talk is gonna be about non-invertible symmetries in the context of holographies. And well, it connects, okay, let me make this joke. So it connects very modern and recent, like, let me say, generation D topic, like non-invertible symmetries, with more like millennial or boomer stuff, like the Myers effect or the Hanany-Witten transition. And I hope I will convey that, and I will convince you that these two are connected via this, holographic and string theory construction in what follows. So I guess to this audience, I don't need to motivate too much why we like symmetries in quantum field theory. But anyway, let me highlight some general motivation. So we study symmetries because one of the questions that we can ask ourselves is to constrain strongly coupled phases of quantum field theory in terms of some symmetry realization. So in other words, whether we can characterize all phase transition in terms of some symmetry or symmetry breaking, and in particular, some in terms of order parameters for this symmetry. So this is a bit of the Landau paradigm, or better the Landau fantasy. And if we rely on just standard symmetries, we know that this is not possible. So, and then one of the motivations to generalize this notion of symmetry is, to try to answer this question. And one kind of question that this generalization of symmetry could answer is the confinement in Yang-Mills theories, where now the order parameter for an higher for symmetry becomes the Wilson loop, and the different phases are characterized by whether the Wilson loops take perimeter or area law. Moreover, for these generalized symmetries, as we all know by now, they have like nice Toft anomalies, and we can try to, by Toft anomaly matching, we can try to constrain the strongly coupled higher phases of quantum field theory, whether the theory is described by its gapless, so it's described by CFT or a free theory in the infra-red, or it's a gap topological quantum field theory. So what we learn by the generalization of notion of symmetry is that basically any symmetry is characterized by a topological operator, and the other way, any topological operator that characterizes a symmetry. So the first generalization is indeed in codimension. So we can take, instead of just codimension one topological operator for standard symmetry, we can generalize to the higher codimensions to define higher form symmetries. And we can also start fusing these topological operators, and when they fuse, they can create a higher codimension topological operator. And this means that the symmetries of different degree mixed is in what is called an higher group structure, or higher group symmetry. So these are two generalizations of the standard notion of symmetry that basically derive by the fact that we have that symmetries are defined by topological operators in quantum field theory. But the generalization I want to focus today is this generalization on symmetries being non-invertible. So meaning that the fusion rules for the topological operator are not, so you don't have just a single element on the right-hand side, but instead you have a sum of different elements. And in particular, this means that—
Sorry, Fabio, there's some kind of weird extra noise from maybe your headphones or something.
Oh,
it's like a crackling noise. I'm not sure where it comes from.
Okay, let me try this. Apologize for the technical issue. What about now?
Yeah, maybe that's better.
Is it
Thanks.
better or worse?
Yeah, I think it's probably better. I mean,
Can you hear me?
Yeah, let's continue. Thanks.
Can you hear me now?
Yeah, but now I can't see the slide. Yeah, okay, slide.
Okay. I don't know what's going on. Let me try to connect to the table instead of.
Yeah, it's not about hearing him, it's the extra crackling noise that's coming with Fabio's voice.
Yeah.
I don't hear anything strange either, actually.
Okay. Well, apparently it's again an Oxford Wi-Fi effect, probably. So let's just keep going.
Yeah, now we can't hear you, Fabio. So I think it might be an issue at Sakura's end. Can you go back to the previous setup?
I think it's related to headphones. Do you need the headphones? Can you just unplug it, use the computer audio?
Can you hear me now?
Yeah,
Okay.
let's just continue. Thanks.
Sorry, I don't know whether I solved the issue, but I hope it's not gonna get worse. So yeah, that's in the generalization I'm talking about. I want to talk about today, and well, you probably all know this by now, but you know that in this case, when you have a sum of elements on the right-hand side which are indecomposable, meaning that you cannot write the actual element in terms of a sum of other elements, this means that there is not every element has an inverse, and this is why we call the non-invertible these symmetries non-invertible. So we might think that these are like exotic or sporadic symmetries. Yeah, by the way, these symmetries, they fit in a very nice mathematical and language, which is called categorical symmetries. But anyway, in physics, they are not sporadic, and they show even in 4D QED, where we have a classical U1 chiral symmetry with an ABG anomaly, which means that the symmetry is not realized quantum mechanically. But what we discover is that we can define new topological operators that basically are the odge or the exponential of the odge of the current, start with the fractional quantum Hall effect, a 3D Chern-Simons theory coupled to the to the vector field of to the flavor symmetry of dual to JA. And what we get is that this topological, the price that we have to pay is that these topological operators define a non-invertible symmetry, meaning that there is no inverse candidate for this D1 over N. So I won't go into the detail of this construction, but this is just to motivate why we study these non-invertible symmetries, that they give some very nice results, which were described in these 3 papers. One of the results is that using non-invertible symmetries, and like the fact that the symmetry is realized also in the infrared physics, you can constrain the coupling of the pion, the topological coupling of the pion Lagrangian with the vector field, with the U1 vector field. And you can also, in extension of standard model, by breaking this non-invertible symmetry by non-perturbative effect, this can lead to exponentially small neutrino masses. So these are very nice physical applications in 4 dimensions, not to mention like application in lower dimension, which have been useful. And yeah, I hope I motivated enough why we like non-invertible symmetries. So let me go more in detail into the setup of and the specific, subject of this talk, which is non-invertible symmetries from holography. So before going to the holographic construction, I will describe briefly the setup of the non-invertible symmetries the specific non-invertible symmetry I'm talking about. And then I will derive these non-invertible symmetries from supergravity and from the brane. And if there is time, I will describe something about the infra-red physics and domain wall physics that we get from supergravity. So I apologize with the people that already heard the iteration of this talk many times. So, but let me go through the setup again. So let us consider a four-dimensional quantum field theory, which I call T. And this quantum field theory, so I want to keep it general for now, as this set of operators, so a set of local operators, so described by a set of local operators, and a set of extended line operators defined on a one-dimensional subspace of the four-dimensional space where the space-time where the QFT lives. Now, I assume that this theory has a 0-4 symmetry, which I specify to be Z2M, so the cyclic group of order 2M. And this 0-4 symmetry is defined by codimension 1 topological operators, which are denoted by D3 because now they're defined on a three-dimensional subspace of the four-dimensional space. And they act on local operators with this 2M root on unity in this way. So this is supposed to be the same mode, by the way. And by the way, they also satisfy this group law. So if we fuse D3L1 with D3L2, this will give D3L1 plus L2. So this is the standard group law for Z2M. We also have a 1-4 symmetry. Now the 1-4 symmetry is defined by codimension 2 topological operators, is acting on line operators with this M root of unity. And D2K, again, they satisfy this group law fusion rule, which says that D2K1 fused with D2K2 gives D2K1 plus K2. Moreover, this theory has, I want this theory to have a mixed anomaly, and this mixed anomaly is written in terms of the background field for the 0-4 symmetry, which is a Z2M background field, and the 1-4 symmetry background, which is the B2 field, which is in Dm. And this is an anomaly because we have a fractional coefficient in front of this 5-dimensional action, which realizes the anomaly of the 4D QFT as an inflow. And this symbol is just the Pontryagin square of B2. So what happens is that when you insert the defect in quantum field theory, the anomaly pulls back into the defect, meaning that if you shift B2 by its 1-4 symmetry transformation, the D3 pick up a phase which depends on a 4-dimensional space whose 3-dimensional boundary is the 3-dimensional space where the codimension 1 topological defect lives. So now we see that D3 picks up this phase, which is equal to 1 over M times Pontryagin square of B2 over 2, where M3, the space where the D3 is defined, is indeed the boundary of M4. So what we ask, what happens once we gauge the 1-4 symmetry? So I will denote this gauging by small letter B2. And what happens is that D3 is no longer gauge invariant, and we need a new definition of this operator to be like of this topological operator to be gauge invariant. So what one should do is to insert a topological, address this defect with a topological quantum field theory, which we denote by AM(1). And with this topological field theory is coupled to B2 in order to cancel now the gauge ambiguity that you obtain by gauging this, by gauging B2. So by gauging B2, now this term will define a sort of anomaly on the defect, a gauge anomaly on the defect, or the gauge non-invariance of the defect that you need to counter by stacking the defect with this topological theory. And an example of this topological theory for AM(1) is the U1 Chern-Simons theory at level M. And one of the non-invertible properties of N3, so you realize that, so you notice the non-invertible properties by fusing different N3s, but so one of the key properties for this N3 to be non-invertible is by fusing with the transpose conjugate, complex conjugate. And what you get instead of the identity, you get this condensation defect which you can think as a mesh of these D2 holonomy into the three-dimensional space, roughly speaking. But the important thing is this is clearly different from one, and this is why this symmetry is non-invertible. So this was just a review of these many nice papers that appear last year, but that's the setup I want to focus on, and now I will describe how to understand this from holography. So, any question on the setup? I guess you probably have this clear. So good. So okay, right. Before going to the holographic setup, let me be a bit more explicit about the theory that I have in mind. So I've been pretty general now because the procedure applies in general. But the theory I have in mind is n=1 SUM super Yang-Mills with this Lagrangian. We have kinetic term for the vector field and the adjoint fermion coupled to the vector with this covariant derivative D. And of course, the symmetries of this theory are a Z2M symmetry, the zero-form symmetry, which comes from the classical U1R symmetry, which is quantum mechanically broken by a Abg anomaly, and which tests that alpha has to take this value in order to be really a symmetry, also the quantum theory. And we also have a 1-4 symmetry, which acts on the fundamental Wilson line with this root of unity, exponential of the root of unity. And this theory has a mix of anomalies, as we described before, so the same type. So we are really in this setup where we can apply we can study non-invertible symmetries by gauging B2, and so in particular non-invertible symmetry for the PSU theory in this case. So that's the explicit example, and now let's go to the holographic construction. Okay, let me motivate why we need holography. So you might say, okay, this is well understood from field theory, but why we do this holographic study? Well, this is a subject that has been developing pretty fast. So there are already many papers on this holographic setup, and some of my personal motivation to study this from a holographic point of view are that not all QFT have a UV Lagrangian description. So sometimes there are QFT which are difficult to access, and so it might be useful to have a orthogonal description that allow us to access the symmetry question for these quantum field theories. Fusion rules in quantum field theory, as we've seen, they are complicated and they might be hard in field theory, but maybe from holography they have another a more intuitive point of view. And I will try to hopefully convince you that there is a kind of intuitive point of view from the holographic setup on the fusion rules. So categorical symmetries, especially discrete symmetry, seems to be naturally encoded in the framework that needs a bulk. And in particular, what I'm talking about are these Symmetry TFT. And so it seems that you can really naturally define these categorical symmetries and this more generalized symmetry by extending the quantum field theory in an extra dimension and describing topological operators in this extra dimension. And at the end, we also might learn some aspects of gravity, especially in the context of ADS-CFT from these studies of symmetries. So these are very general personal motivation, but that's why I like to study this from this holographic point of view. So the goal is to understand the non-invertible symmetries which are realized holographically in this explicit, in particular in the explicit example, which is related to SUM super Yang-Mills. And the way we approach this question is by constructing a D+1 dimensional holographic topological action from the 10-dimensional supergravity. So what is why we want this? So this gadget, this D+1 dimensional holographic topological action, because this holographic dimensional topological action, D+1 dimensional, is encodes two aspects of the theory in the boundary. So the first aspect are symmetry data, and the second one are anomalies for these theories. So the theory doesn't really specify a single quantum field theory in the boundary, but we need also to choose a topological boundary condition in order to specify a quantum field theory in the boundary. So in general, what we get in the boundary is a relative relative theory which is not just a single theory because it doesn't have a single partition function, but rather a vector of a partition vector, a vector of partition functions. And so we need to pick up a boundary condition in order to specify a single theory in the boundary, which is called also absolute theory. This is not always possible. For example, the famous example is 2,0 theory or the chiral boson in 2 dimensions, where you cannot really decouple the symmetry theory from this bulk theory from the boundary. And so you cannot, generically, you cannot have always an absolute theory in the boundary, but you always have a relative theory, which is connected to the bulk. So in particular, moreover, so the general law is that gauge symmetry in the bulk, they correspond to flavor symmetry in the boundary. And already said that these symmetry theory, they contain the Toft anomalies of the theory at the boundary via inflow. A famous example for this is ADS5 cross S5 in type 2B supergravity. And the symmetry TFT for this is the dual of n equals 4 super Young Mills, SU and super Young Mills. And the symmetry TFT that you can derive from ADS5 cross S5 is given by B2 DC2, where then you have an n multiplying this theory, which comes from the F5 form flux on S5. So you have this, this is the topological coupling that you derive from the topological coupling in type 2B. So the classical equation of motion set these two fields to 0, and this means that what really matters are the holonomies of B2 and C2 in the group ZM because of this multiplication by. So in order to really specify a theory with a global, a gauge theory, the global with a group, so the global structure, the gauge theory, the boundary, and it's 1/4 symmetry, we need to pick up boundary conditions. And the two extrema, so there are many topological boundary conditions that you can pick up here, but the two extremal one, which I want to highlight here, are the one that tell you that B2, so the first one is the one that says that B2 is fixed at the boundary, and C2 is freely varying at the boundary. So here I always separate the boundary condition with the relative theory. But what I have in mind in holography is that you always collapse this boundary condition to the boundary in order to have an absolute theory. So in this case, you have B2 fixed and C2 freely varying. This is the case where you have SUN group. And in the other case, you have B2 freely varying and C2 fixed. And in this case, you have PSUN, which is SUN mod N. So in the first case, the Guco-Witten operator, the holographic Guco-Witten operator are the holonomies of C2, because C2 is freely varying, so you can slide parallel to the boundary, and you can define the Guco-Witten operator for the 1/4 symmetry, the Zn 1/4 symmetry of SUN, by the holonomy of C2 in this way, and similarly the holonomies of B2 for the other case. So this is what happens for n equals 4 super Young Mills, but the holographic construction that I have in mind is the Klebanov-Strasov solution in type 2B, supergravity. So this is given by the near rise of any free brane probing the conifold, which is the cone, the real cone over T11, and T11 is topologically equivalent to S2 times S3. And in the brane construction, in order to have a unbalanced quiver with the rank of the two nodes being different, in the dual theory, we want M d-phi brane on S2. So we want M d-phi brane wrapping S2. So I want to specify the case where n is equal to km. So it's a multiple of n. And in this case, this theory is related to SUM supreme. We have a chain of S cyber duality and RG flow. This means that there is a chain of cyber dualities and RG flow, which connect the RG flow to the infrared of this theory to the RG flow of the SUM theory in the infrared. And in particular, what SUM shares with this theory, which is a bit more than SUM, are the symmetries, the 1/4 symmetry that I want to talk about, the ZM 1/4 symmetry, and the 0/4 symmetry Z2M. And this is enough to really study the dual of this setup and claim that this result is also a valid result for SUM. So the near horizon limit that we take in this case as this metric. So we have a 5-dimensional space with a boundary. So the boundaries are at r equal r0, where r0 is large. And so there should be a minus here. And there is a warp metric of T11. The warp depends on the radial direction. And moreover, the MD5 brane, they become F free flux on S3. And we have also a running F5 flux. So you can also define a fixed F5 flux using page charge, but let me just stick with this F5. So the dimensional, so what we want to study here is that instead of like in ADS5 cross S5, we want to study the dimensional reduction on T11, which is S2 cross S3 of type 2b supergravity. And in particular, we want to look at small fluctuation of the type 2b supergravity field around the Klebanov-Strasser solution. So this is the answer that we made with studying small fluctuation around the background when these fluctuations are indeed small. So any question about the setup, and then I will describe the theory that we get in 5 dimensions.
Sorry, can you clarify why do you have a one-form symmetry? I mean, there is matter in the fundamental.
Right, the one-for symmetry that is preserved is the diagonal TM between.
Okay.
Yeah.
So essentially, there is a one-form symmetry that you engage, and in the IR, instead of having SUN Young-Mills, super Young-Mills, you have PSU and Young-Mills, right?
And here, so this is so there is no global structure specified yet. In order to specify global structure, you need to pick up boundary condition.
Yeah, but
so in
exactly
this case, in this case, you have a VM diagonal one for symmetry, as in this case. So in this case, it's not diagonal, it's the ZM.
So okay, my question was precisely in the whether in the Klebanov-Strasser theory you have different global structure possible.
No, it's the same global. It's the same kind of global structure you have as you have.
Okay.
Yeah, it's so you take it's always the diagonal, or the other global structure that you have is P of both of them. I see what you're asking. So instead of P SUM times P SU3M times P SU2M, you get P SU3M times P of everything. You see what I mean?
Yes.
Yeah. I don't. Yeah.
But no. So just because I'm confused, is in this case, I mean, you don't have PSUN of both, but when you flow to the IR, while if you choose SUN and SUN, you flow to SUN super Young-Mills. In this case, I would expect that you flow to PSUN super Young-Mills.
Yeah, you flow to PSUN.
Okay, so the IR is not really gapped.
No, it's not really.
Okay.
Yeah.
Okay, perfect.
Yeah.
Thank you.
So so by studying this small fluctuation, then the topological action that we obtain. We obtain a more general action. So there are also kinetic terms which are subleading once we send the radius to infinity, because they contain higher derivatives. And the topological action that we get, where we also ignore the fact the term that are proportional to n which runs, is this one. And this is indeed enough to describe the symmetries of this theory. So, in particular, we have A1, which is the Rib vector. So it's the U1 isometry vector of the T11 metric, and this is dual to the R symmetry in the boundary theory. We have a G2B, which comes from S5, and this G2B is basically the dual field for the background of the one-form symmetry. And moreover, we have a T3, which is the reduction of C6 on S5. So you might have seen this action in these papers in terms of other field, but you can dualize this field to get to this action. And moreover, by studying the equation of motions or the Bianchi identity, what you get is that you get this condition that tells us that these two fields, there is a B here, but these two fields are in this are the background, the dual background for the one for symmetry and the 0. So this action is written in terms of a continuous supergravity field, and so the BF term and the supergravity couplings, as I told you, they can give rise to this condition which discretize the field. So no global form and no one specific one for symmetry, or no global form and no specific quantum field theory has been picked so far. So we need to still specify the boundary condition and the topological boundary condition for this theory in order to pick up, a global form, a gauge group of the boundary theory. And for example, in this case, will be SUM versus PSUM, n equals 1 super n mills. Okay, so this is the supergravity action, and now we want to study the symmetries of these coming from these actions. So the strategy that we implement is a systematic strategy which was first advocated in this paper. So we consider the radial direction as a Euclidean time direction, and then we decompose all the fields into this time component times a spatial component, So this will depend only on, so we now the space has this radial direction, and it's foliated. So we have these slices which are 4-dimensional, and this it's only a 4-dimensional field, and this is the time component. What happens is that the Lagrangian decomposes in this way. So we have A1, the Lagrangian will depend on A1 and A1 dot in this way, but we also have an additional term, which is a Lagrange multiplier term. So we have, since the Lagrangian doesn't depend on A dot 0, it means that these A0 are just Lagrange multiplier for a combination of the other field. And by varying the Lagrangian with respect to the Lagrangian multiplier, what you get is this constraint, which are the Gauss law of present in your theory, the Gauss laws present in your theory. So the Gauss laws, they implement a small gauge transformation on a spatial slice, and which is M4. And what happens is that the small gauge transformation are indeed implemented on a spatial slice by these operators, this Gauss law operator multiplied by their gauge transformation. So yeah, so this exercise is an exercise that maybe is better known in Maxwell theory, but it's the same. So in Maxwell theory, you decompose the Lagrangian in this way, and what you get is the Gauss law nabla equal to 0. So basically, we define gauge invariant operator, which implements the gauge transformation on a spatial slice. Good. So I want to focus on one particular combination, one particular operator, which is interesting in this from the 5D bulk topological action that I constructed before. And this is these operators, which is DC3 plus G2B square over 2M. Where I recall that G2B is a flat space when multiplied by M. It is a flat field when multiplied by M. So we need to define a genuine operator at the boundary. So a genuine operator meaning that at the boundary, what we have is that this G4, it's equivalent to D of a D3 operator at the boundary. And we need to study this subject to those possible topological boundary conditions. So whether we take C3 freely varying or C3 fixed, and the same for G2B. So since we are interested in cases where we have a 1-for symmetry, we will always assume that C3 is freely varying and A1 is fixed, meaning that A1 will define the background for the Z2M field, for the Z2M 0-for symmetry at the boundary. So of course you can do also the other way, but this is not, I don't have time to review that case, but it's also an interesting case to understand. So, and we face many possibilities, but the possibility I want to focus is the first possibility is when we keep G2 fixed or Dirichlet at the boundary. This means that this number, G2B over 2M, is just a C number. And the actual operator that defines the symmetry is these holonomies of C3. And in this case, this operator is invertible, and it generates the Z2M symmetry of SUM super EM. What happens when G2 varies freely at the boundary? It happens that this integral now is not well defined anymore because it's not a C number. And you have to think about this as a sort of D of an improperly quantized Chern-Simons function. So usually Chern-Simons function comes with an integer coefficient, but in this case, they don't have any. In this case, it doesn't have an integer coefficient. So we need to, properly define this function. In order to properly define this function, what you do is you add an auxiliary field on which you path integrate over, and you add and you modify the action in this way, such that when you integrate out A, what you get is that G2 is flat, and you get back to this action. But what it means that is now this new topological operator defines a non-invertible symmetry because it contains basically this topological quantum field theory. And when you fuse N3 with N3 dagger, you don't get back to the event. So this is the way to get the non-invertible symmetry from this holographic construction. And to summarize, we have two sets of fields. We have a C which are paired, C3 and A1, and we have another set of field which is B2, G2. It's a more, in particular, it involves basically G2B and B1. So forget about this other field. I just presented the action in terms of G2B. So what happens is that since G2B appears in this Gauss law, it means that this, in order to specify a proper topological boundary condition, you need to collide these two slices before colliding to the boundary and pick up a theory, because in this Gauss law, the field related to the 0-4 symmetry are combined with the field related to the 1-4 symmetry in this way. Anyway, this was just a summary of the setup that we have. Okay, so let me go to the second part of the seminar, which is symmetry generators from branes. Again, so this is not completely unrelated to the supergravity part, but it ties very nicely with the supergravity part. So let's pick up this Gauss law. So we have this Gauss law, which is DC3 plus G2 squared over 2M. And we first need to understand what C3 is. So C3 is the dual of C0. So C0 is the potential of type 2B, which comes from the field strength F1. F1 is DC0, and F1 is just the expansion of F3 on the volume of the two sphere, where the two sphere is in T11. So we expand F3 on T11 on its two sphere, and what we get is F1, which is DC0. And C3 is the dual of C0, meaning it's the dual in 5 dimensions. In 10 dimensions, the dual is actually C6, which is expanded along S3. So if you expand C3 along S3, what you get is C3. And this is basically means that it's electrically sourcing a D5 brane on S3. And the proposal is that this D5 brane wrapping S3, but also extending on M3 on the spatial slice M4, which is at a particular R value, realize this defect, the symmetry defect, the 0-4 symmetry defect. So this is a picture of what is going on. So we take a slice, an M3 slice of the 4-dimensional slice at R equal R at a particular position in R. And I want to stress that these branes in this setup are non-BPS. So these will be BPS in the 4 conifold, where the S3 is blown up at the origin. But in this case, when the sphere is at basically at infinity, this configuration is not BPS. Okay, so let's go along with this proposal. Let's compute the low energy effective action of the D5 brane. So the low energy effective action of the D5 brane contains two terms, contains a DBI action and a West-Lumino action. So DBI action, you want to think about it as a sort of a generalized kinetic term, and the West-Lumino action is the topological part of this action. So the DBI part depends on the determinant of the metric, and since it depends on the determinant of the metric, you can compute an effective tension for the DBI part, and the effective tension at M3 in M4 at this particular R value is proportional to this R value to the cube. What this means is that when we take the R going to R0 and then going to infinity limit, then the DBI action decouples because the tension is infinity. And this means that the non-topological part of the action is basically frozen. So what we are left with is just the topological action of the brane, which is the West-Lumino term. So the West-Lumino term has this, bulk potential expansion. So it's coupled to B2 and Ramon-Ramon potential, but it's also depending on a A1 field, which is a field that is dynamical on the gauge on the brane, and it's a U1 gauge field on the brane. And we want to compute this action indeed in the regime where we collide these to the boundary at infinity. Good. So we perform this computation. This is an easy computation. You can integrate. We can expand the Ramon-Ramon field on S3, and you have to remember that you have F3 flux, which is proportional to the integer m. What you do is then an integration by part, so you get these two terms, which are the interesting terms, and you do an integration by part to get the fluxes, and at the end, the result is the following action. So you have C3 plus the Chern-Simons action in terms of this A1, and then A1 coupled to dB1, where B1 is again a bulk field, which is the expansion of C4 on the volume of S3. So this is the important thing is that you get this action. It's containing this Chern-Simons term, but it's containing also this other term, which is important. Okay, so any question on the derivation of this action?
Yes, I have a question. Hi.
Hi.
Can you repeat what you said about BPS versus non-BPS a couple of slides ago?
Right. So this is so the D5 branes. So the D5 branes. So in this is the brane that is wrapping the S3 at infinity. It's not wrapping the S3 at the tip of the conifold. So if in the deformed conifold, you might. I mean, you very well know that if you wrap the S3 on the deformed S3 sphere, then this is BPS. But it's not the case, since it's not wrapping a minimal cycle volume when it's at infinity, this is not BPS. That's why it's not BPS, because it's not wrapping a minimal volume cycle in this case. So it's wrapping the sphere at infinity.
Well, at some point you send this the other question is related to this. You are sending this D5 to infinity.
Yeah.
So, and this is the argument you use to claim that it becomes so to say frozen, so you can forget about the DBI, etc.
Yeah, exactly.
So which kind of theory are you probing at that scale? SU infinity cross SU infinity? What theory are you probing? I mean, the cascade is infinite. I mean, never stops, no?
Yeah, the cascade never stops, but
so
I mean,
I
agree.
IUV, no, in the technique, in the use.
I agree, but this is what you really consider here is just the D5 brane sector, which is basically what captures the SUM sector of the brane of the setup. So even if this space is not really ADS, it's really close to ADS. So you can really look at the theory close to R0, which is large, and you can look at the the sector which is which describes the D5 brane wrap on S2 sector. That's what I mean. So that's the important part that capture all these symmetries. Is the D5 brane on S2, which are MD5 brane on S2, and it's the flux sector described by F3 on S3, which is equal to M. And I mean, you can perform, you can study the. That's what really matters in terms of the symmetries. The fact that N is running and you have this infinite cascade, it's not very meaningful for this case. But at the end, I mean, this part of the action, which is a truncation of the full action, is only depending on M. It's not depending on M.
Well, that's okay. Okay, it's okay. It's okay. Thanks.
Fabio?
Yeah.
Can I ask you, can you show me again the very last best sumino action you obtain after you expand this exponent? I think it's in the next page.
Yeah, this one, right?
Yeah. So let me ask you this. I was trying to follow this. The A1 wedge F5 in this integral disappears, right? I'm looking at the previous to last line.
Well, not if you expand. You also expand, F5.
I see.
F5 is contains more term, but the term that is relevant here is this expansion, this B1.
I see. So are you going to integrate the 5? Okay. Yes, I see.
Yeah, this B1 is basically coming in the Stuckelberg pairing with the G2B, with the G2B for the dual field of the 1-4,
okay,
which is important.
This object, maybe this is follow up from Mateo's question. This object is kind of a domain wall-like object, right? Because occupies 2 + 1 dimensions in Minkowski. Am I and there's 3? Am I thinking it correctly?
So in terms of space-time, in terms of dimensionality, I agree, but I want to stress that this is very different from space-time. From the domain wall. So the domain wall in this, in the Klebanov structure, the dynamical object that takes from one vacuum to the other. So I will comment this at the end if I have time.
Okay.
But this object is really the brane at infinity. In terms of the symmetry that you're interested in, this is a.
Sorry, Fabio. Sorry for the stupid.
Yeah.
This is really a poor man question, but. Does this brane at infinity stays there? It's not BPS.
Yeah, it stays there. So if you compute in the Klebanov cycling metric, which is not the full solution, but it's still the solution which is valid for R0 large. Even in the Klebanov Stassel metric, if you do the R large limit, you get Klebanov cycling. If you do that, the computation of the potential of you can do a probe computation of the potential, and that goes like minus the tension. The potential, and minus the tension means it's minus R3, which has a sort of runaway to infinity. That means that the brane really wants to stay there at infinity in this cell. This is because it's not BPF, right? Okay. If you do a probe computation in the other regime, the brane wants to go to 0.
Yeah, that was my point.
Yeah. But in these regimes, in the Klebanov-Zeitran metric, in the Klebanov-Zeitran background, this goes with like minus R3.
Okay. Thanks.
Okay, so having derived this action, so A1 is always dynamical on this action. So we need to do Pi integral over its configuration. But what we're interested in now is what happens to the other field. Also, we want to assume that C3 is always dynamical at the boundary, so it's always freely varying at the boundary. So we also assume that. And we want to study what happens for different behaviors of B1. So B1, I want to stress that this Stuckelberg pairing with G2B. So this is related to basically the 1-4 symmetry. So if B1 freely varies at the boundary, what we obtain by rearranging this action is a D1 Digraph-Witten theory, which is a trivial Digraph-Witten theory, meaning that the topological dressing is trivial. And this relies on an invertible defect because it's just the holonomy of C3 at the end, and it's the dual of SU and superunit. When B1 is fixed and is equal to 0, because it comes in Stuckelberg pairing with G2B, then this means that this action, this Chern-Simons action now, it's rather non-trivial, and it gives the topological dressing, which also was derived using field theory. And in this case, we derive this non-invertible defect just from from this brane construction. And it's not invertible indeed because it contains this topological dressing. So let me quickly go through over some properties of this non-invertible defect for PSU theory. So one question is, can we derive fusion rules from branes? And can we construct, for example, the double, twice this non-invertible defect? So from field theory, we know that this is true for M mod. So we have this fusion which fuse two non-invertible defects into this N2 and 3 non-invertible defect, but now the coefficients are not number, but are topological quantum field theory, which are decoupled, meaning they don't couple to the same B2 field as this defect. So this is true only for M mod, and for the other M generically is not known. And a puzzle is what we can try to do this from this brane construction. We take two branes, we put on top of each other, two D5 branes on S3, and what we get is a U2 Chern-Simons theory at level. However, this fusion we suggest to us that what we get is a U1, the U1M tensor product with U1M going to a U2M. But this is not good because we know that in this fusion, at least for M mod, both on the right and the left-hand side, we have abelian anions, so abelian topological lines, which, so we don't have non-abelian topological line as in this U2. So this raises a puzzle. Why we get a U2 from this brane, but from fusing this brane? Well, it turns out we haven't considered the brane dynamics. And in particular, the brane dynamics before really going to before sending R0 to infinity. So the dynamics of a non-abelian brane stack is given by the orthogonal fluctuation of these brane stacks. The orthogonal fluctuation are matrices. So if we have K D5 brane, these are UK matrices, and the dynamics of this brane, this fluctuation is captured by this action. So where here we have a non-trivial B field, which gives this important coupling in this action. So, this xi describes the orthogonal fluctuation, and in particular, a simplification that we have in this case is that luckily, when we send R close to R0, the orthogonal space, which is the radial direction, the S2 of T11, form a flat space. So we don't have correction coming from the matrix, and close to R0, we really have a flat space orthogonal to the D5 brane. So the equation of motion are given by this expression. So we can solve this equation of motion, and what we get is the minima static configuration is given by K times K matrix representation of SU2. So we have K times K matrices, which are reducible representation of SU2. But this is not other than the Myers effect. So in particular, there is a dielectric effect caused by the presence of the B2 background on S2 on this orthogonal space. And this means that the phi brane, they puff up, and the equivalent configuration is given by a single D7 brane on T11 with a F2 flux on S2 with K unit of F2 flux on S2. So you can do a computation again for the D7 brane, a single D7 brane with these flux, and at leading order you get the same vacuum value for the case with for the minimum of this non-abelian brane action. So we can for K equals 2, the 7 brane action, we can integrate the 7 brane action on T11, and what we get is the defect for this brane, the topological action, this brane when sent the brane low energy limit action is that survives is only this topological term, and it's this action that we get, which is now abelian. So we have hope to match with the right fusion rule, and in particular, what we show is that this action via field redefinition is equivalent to the left-hand side for any M, and is equivalent to the right-hand side. We only check this for m equals 2 and m equals 3, even if this is not really the holographic regime, but you can trust, you can really assume that this is true for a small n, and you realize that this is actually equivalent to the right-hand side of this equation for m equals 3, and it's a bit different for m equals 2, but you can also check that this is true for m equals 2. So this is what we get from this brane action, and from as the Meyer effect plays a really important role in this story, because it really abelianized the action, and this was really needed to match these fusion rules. Another hallmark of non-invertible defect is the action on operators present in the theory. For example, in 2D Ising model, we can sweep across the non-invertible defect a spin operator, and this you get the mu operator connected with the Z2 line on the right-hand side. So what the hallmark of non-invertible symmetry is that when you do this, this doesn't preserve really the dimensionality of the operator, but you get a higher dimension operator connected between the local operator and the non-invertible operator. So this is what happens in defect theories in the 2D Ising model. Similarly, for PSU n equals 1 super Hamiltonian, the action on a non-invertible defect on the top line is very similar. Indeed, we can sweep across the non-invertible defect the top line, and what we get is a flux, a tube of threaded by flux, which connects the non-invertible defect with the top line. One way to see this is indeed to gauge the one to see that once you gauge the one for symmetry, you really add a counter term on the right hand side. So the non-invertible defect divides the 4-dimensional space into 2 parts, and on the right hand side you can add a counter term which depends on B2 square in this way. And what you get is that the top line on the right hand side is not gauge invariant once you do this shift. So you need really to dress this operator by B2 on sigma, where sigma is this cylinder that connects H with the non-invertible defect. Okay, let us recap in terms of the brane in the Klebanov cluster background. In terms of the Klebanov cluster background, what these objects are in terms of branes. So we have a top line, which is the D-free brane, wrapping S2 and extending on the radial direction and on time. And the non-invertible defect is extending on time plus other 2 directions, and it's wrapping S2. We can immediately realize that by chain of T and S duality, this is dual to the NS5D5 Hanany-Witten brane system. In particular, charge conservation implies that the total linking number between the 2 branes, so the D5 and the D-free brane in this case, is conserved, meaning that if we exchange the position of the 2 branes, the linking number must be the same. The linking number is computed by flux on the orthogonal space, where the orthogonal space is denoted by M2 S3, and in this case, for S3 is denoted by M1 times S2. So this is a way to computing the linking number. And what you realize once you exchange the brane is that the linking number is not conserved. So what you really need to do is you need to insert F1 strings, which extend on the direction where the 2 brane links. So the D5 brane and the D-free brane, they link in the X-free dimension. And you need to insert F1 brane connecting these 2 strings in order to really conserve this linking number. And what this is just the Hanany-Witten transition. So the Hanany-Witten transition is indeed a consequence of the charge conservation or conservation of the linking number. And when you exchange the brane, you create an F1. And in field theory, this realizes the action of the non-invertible defect on top line. And in particular, you get that the top line on the right-hand side are connected to the non-invertible defect by this flux operator. And this flux operator is what you get on the F1 action once you send R to R0 and R0 to infinity. So this is really the topological term survives for the F1. Okay, so maybe I can go for 5 minutes more. Is that okay?
Yeah, that's good.
Let me tell you how we can get the R phases from supergravity. So this is a bit of change, but right, I want to stress that it's a bit different from the construction of the defect. So the holographic solution now here becomes the deformed conifold, which is denoted by T star S3. So this is the deformed conifold, which has an S3 free cycle calibrated within minimal volume free cycle. And the IR physics is defined by the symmetry enriched topological theory that can be derived also from supergravity in a certain way. So you can derive this for the action from supergravity. And what you get is basically this topological action, which contains a topological term phi dc3, but it contains also phi db1 square and a Lagrange multiplier multiplying db1 plus mb. So what this action describes is it describes M vacua, and it describes spontaneous symmetry breaking from Z to M to Z2, meaning that the phi now take value as integer, as P over M integer, and the phi value we specify a vacua for this theory. And in the far infrared, we also can also vary this action with respect to Lagrange multiplier, and what we get this equation. We get this equation that set db1 equal to m minus b2. This is crucial in order basically to match the Toft anomaly that you get that you have in this case. But what it also captures this action is basically the domain wall physics, because the domain wall from the string theory construction can be seen as S3 wrapping the T star S3. And in this case, since R is small, so we are in the regime of the solution where R is small, the deformed conifold metric, and the D5, the tension depends with R3, where R3 is now small. So what we need to do here for this action, we need to study the boundary condition for B1 and B2. And you can do that. You can study the boundary condition for B1 and B2 in order to, of this action, in order to understand, the infrared, what is going on in the infrared. And for SUN, we have B2 fixed. So the domain wall, SUM, the domain wall is a free, the domain wall theory contains a 3D Chern-Simons theory, which matches the anomaly. So you remember that SUM case has this anomaly. And it needs to match this anomaly. And indeed, we have this Chern-Simons theory. This is the theory on the domain wall. So we have C3, but we also have this Chern-Simons theory. But in this case, the brane is not frozen because the dynamics of the brane, since the tension is small, is really, is really relevant in this case. For PSUN, we have now that B1 and B2 freely vary. So what we get in this 4D, so the 4D theory now contains a ZM discrete gauge theory, which is given by this part of the action. So this is what is expected for PSUN. But it also contains the information about the domain wall. And in this case, the domain wall, the topology, so this Chern-Simons action trivializes because B1 is dynamical, so we do path integral over B1, and what happens is that the domain wall theory is the Z1 Diagram-Witten theory. We can recast this theory in terms of this matrix, and this gives that the domain wall theory contains only C3 as field, not the Chern-Simons action, as was basically predicted theoretically in this paper. So, right. So this was what happens in the infrared.
One question on what you were saying, sorry. So
Yeah.
You mentioned like the theory that lives in the domain walls is Acharya-Vafa, but this theory is the one that you had before you use the Myers effect to compute the fusion rule, right?
Yeah, this is a single brane.
Right. But if you put more branes, I think I remember in the Acharya-Vafa paper, what you expect is to have UK level n.
Right, that's what you get.
Right. So are the two things compatible? What like the fusion rule for the topological defect and this statement about the field theory that lives in the domain wall?
So the Myers effect is really an effect that happens in the regime where you have not the Klebanov cyclic metric, where you have the B field threatening the orthogonal sphere. So in this case, the solution is a bit different. So we haven't checked this, but I'm not sure. I think it doesn't occur in this small R regime. So it's really the UK, the the non-abelian theory in this case.
Okay.
But I haven't checked, so I'm not 100% sure. So that's indeed something that could be checked.
So, and I have another question. Sorry.
Yeah.
Right. So the D-brane that is described in the domain wall is the same one that is described in the topological defect. But before you said that there is like a runaway potential for this D-brane at the boundary.
Yeah, again, this is in different regimes. So in the metric
right. So, but should I expect that the D-brane at the origin can somehow tunnel and decay to the boundary? Because
no, I don't think that's the right interpretation. No, okay. This is a different regime. So yeah, they really are separated by, but yeah.
Okay, thanks.
Right. So let me just quickly go through. So you can do the same for n=4 duality and triality defect. So we all know that there is a non-invertible symmetry at the self-dual point of n=4 super means. For example, SU2 at tau equals I as a non-invertible duality defect. This has been studied in this paper. And you can realize this holographically. This has been subject of many nice papers, which extend the BF theory that we have in n=4 super means with this sort of covariant derivative now acting on the B field, since the SL2Z, so since the discrete symmetries, the zero form symmetry is a subgroup of SL2Z, then it acts on the B field. So you really need to change a bit the theory. So these are many complicated description, but this is pretty schematic, and so you can do that in this case. And thinking about it, in the ADS5 cross S5, the type 2B axial diluton correspond to the complexified gauge coupling, tau. And tau is acted upon SL2Z from type 2B, and the generators of this, so the SL2Z matrices that act on tau are basically the monodromies of the 7-brane, which in this case wrap S5. So we can construct this non-invertible defect again by 7-brane wrapping on S5, and now extending on M3 on which is a codimension 1 manifold into this slice M4 of ADS5. And by studying a 7-brane monodrome, the 7-branes, you really, at this fixed tau coupling, this is for duality, this is for triality, you really get these matrices, which are the monodrome expected for that generate the subgroup, the duality and triality defect subgroup. Another evidence that is a good proposal, the 7-brane good proposal, is the action on the Toft line. Again, the hallmark is that the action on Toft, the operator is not doesn't preserve. So the sweeping across the non-invertible defect means that the dimensionality of the operator is not preserved, and these indeed do a Hanany-Witten transition. So the PQ strings, which are the Toft lines in n=4, do a Hanany-Witten transition with the 7. So this is another evidence that the 7-brane proposal is the right direction to realize this in terms of brane. And yeah, I hope to report this result soon. So let me conclude by saying that we have constructed a bulk action that corresponds to the symmetry TFT for n equals 1 SU and super mills. We constructed non-invertible defect via Gauss laws in the bulk action, and this bulk action is really derived from the Klebanov-Strassel background, but really truncating into a sector which takes into account only the D5 brane mapping S2. So really the sector that is dual to the SUM part of the Klebanov-Strassel solution. So we construct a non-invertible symmetry defect from branes in the Klebanov-Strassel background. So we have computed some fusion rules, which make sense only when the Myers effect is taken into account. And moreover, the action of the Toft line of the non-invertible defect on the Toft line is very well captured in this brane construction, which is key in order to do this mapping by an Hanany-Witten transition. And finally, we have discussed some IR phases from holography in terms of domain wall physics and Bakwan due to a spontaneously broken discrete symmetry. So one thing that we can do is to understand what is the fusion, and this is something that we are thinking about, that tachyon condensation can realize the fusion between N3 and N3 dagger. So we're taking a tachyon condensation which comes from brane anti-brane and fusing them together, and only retaining the topological coupling to the bulk field seems to be the right direction to understand this fusion from tachyon condensation. So another thing would be to understand more fusion from this brane. So there are other examples of holographic and string theory engineering which similarly realize the non-invertible defect in terms of brane. And something very interesting is that whether we could construct holographic and brane description for non-invertible symmetries when non-invertible symmetries take value in Q mod Z instead of a discrete group. And finally, this is a more mathematical question. It would be nice to understand whether there is really, a general mapping between brane and, K theory to these categorical symmetries. And with this, I thank you for the attention.
So thank you, Fabio, for this excellent talk. Are there any other questions from the audience?
Sorry, I have a question on the computation of the fusions. Why do you think that the mechanism behind the non-invertible fusion rule of N and then dagger should be different from the mechanism behind the fusion of N with N?
You mean, well, in duality, this should be the same.
Yes.
If you ever did, yeah. I mean, you can really check. It would be nice to check. This is something that so tachyon condensation is. It's not that it's a different mechanism. It's a mechanism that appears in string theory when you fuse brane anti-brane, and you want to understand whether that realize, this case. But I'm not saying that these are different mechanisms. At the end, I agree they should be equivalent. It's just you want to, understand this tachyon condensation. Why it gives this, and then if it's equivalent in case of duality, you also want to understand that as well.
Okay, so this tachyon condensation should be should take place only when you are fusing a defect with another defect in such a way that on the right hand side you get condensation defects, right?
Yeah. So tachyon condensation is something that you get in string theory when you collapse a brane with anti-brane. So that's why you get a tachyon potential, which you get a tachyon profile which condense. And
also I have another question on the fusion of N with N, because you showed that by naively stacking the TFT you get the wrong result. And also in the case of duality defect, what we found in our paper is that indeed you don't have to just stack the TFTs because you have to take into account the contribution of the bulk. And if you do this, you get the right result. So I was wondering whether this is related to the mechanism that you found, because it is somehow an interaction with the bulk In our case, it was just we consider just the simplest setup of n equal to 4 super Young Mills. So the bulk theory is simple, and essentially by taking into account the coupling of the TQFT living on the defect with the rest of the bulk, you can correct the naive fusion rule and you get the right result. So
yeah, can you be a bit more specific? What is the correction that you?
The point is essentially that you have the TQFTs, and but the degrees of freedom of the TQFTs are coupled also with the degree of freedom of the bulk. So when you put the two defects together, you don't just have to sum the actions, because they are coupled with the degrees of freedom living only on the bulk. And if you do the computation properly, you have extra contribution in the computation of the defects, which correct the naive result. So it's also a contribution coming from the bulk, as in your case, because you are essentially taking into account the contribution of the brane. So I was wondering whether this could be related.
Yeah, in general, it could be. For this case, since we think these are 7 branes, I find it hard to believe it's really, maybe it's another effect, maybe it's not my effect. That's what I mean. But it's I agree. Generically, it's the interaction with the bulk that does this. So I agree.
Okay, fine.
So if there are no other questions, let me stop the recording and then we can discuss.